It's very obviously language specific, because the instrumentation is tied to the language. It's very intrusive. You clearly perturb and modify your software, and what you're testing typically is done on the host. So it's doubly intrusive. So the code that the binary code that you're running runs on the host, has nothing to do with the target code. And so typically you're required to run your test twice. One on the host to get structural coverage information, and one on the target uninstrumented to show that the outcome of the test are the same. So that this intrusiveness is not that intrusive after all. When you're instrumenting the object, and for instance the GCC compiler does this. Basically when you generate code, it instruments the object code to get coverage information. It saves it into a log file, one per object, and then as you run your various tests, it accrues the coverage information on the log files and consolidates the info. Well, it's obviously, the benefit is that is independent of the programming language. It's done at the back-end level, so whether you do it for Ada or for C, it works the same way. It's compiler dependent, obviously. This is works in this case for GCC. It's, again, very intrusive, and it only works when compiling for the host. You need a way to get the information back from where you're running. And in the case of GCC, this is typically done on the host. It needs to save things on the file. And as it currently is done, it's unsuitable for level A of DO178B. When you're extracting the execution trace from the hardware, well, you have programming language independence, you have compiler independence, it's non-intrusive, you can obtain coverage info on the actual executable or the objects that will run and that are running on the target. So these are all good points. Unfortunately, it has a couple of downsides. It provides object level coverage. How do you go back to your sources in the presence of compiler optimizations? How do you achieve MCDC? That's far from straightforward. And it can be slow. For instance, if you're single-stepping, the CPU is very slow, or you need extra hardware. And in any case, you need the target hardware. And you need a connection between the target and the host to get back the trace information back on the host. So, given this context, I can now tell you what we're doing in project coverage. And the name of the tool that we're working on is XCOV. Our starting point is that there is today no open source tool set for doing code coverage that works in the DO178B context. GCC has the coverage at the object code level when it generates code, but that doesn't work for DO178B, at least not for level A. The other thing is that it would be nice to have cross-fertilization between the DO world and free software and open source. And I'll tell you more about it in the next part of the presentation. The key point is that the DO world has long recognized that software is not just the sources. Software is not just the sources, a lot of other things. And so, and the free software and open source world have come to find certain things that the DO170B world hasn't embraced yet that are very interesting. So how can we have cross-fertilization between the two? So if you take Ada Core, we are a company that's doing 100% open source. We are in the world, DO178B and 78C world. We're part of the committee. Cyril specifically is part of the one of the subgroup of the DO178C world. And it's a very natural thing for us to look into this. And our starting point was, it would be nice to have a tool set which is open source that provides the ability to get DO178B code coverage metrics and offer both source level and object level coverage. and leverage on this as a first building block for cross-fertilization opportunities. As I said, the source code isn't everything when it comes to software. So we looked at the three approaches, and the one that was the most promising was working for execution traces, because it was programming language independent, compiler independent, unintrusive. You can get coverage info on the exact executables or on the exact objects that would run on the target. And so we needed to solve these two downsides. First of all, it can be slow and it needs hardware. So if you don't have the target hardware yet, you can't start doing coverage analysis in this context. And the fact that if you're running on the real hardware, you need a connection between the target and the host. And then I'll talk about how we address this issue. So how can we get rid of the hardware? That was the first point. Well, we looked around, and it was sort of an obvious thing. Virtualization was the thing. VMware is an example. When I say virtualization, emulation is in the same realm, and QEMU, Quick Emulator, is another example. So today you can emulate or virtualize hardware. You can have Linux run on Windows, Windows run on Linux. Why couldn't we do the same thing for target hardware that's used in embedded systems? The other question is, how can we achieve source level coverage in a object world? And so the ideas were the following. One, don't instrument the code. Instrument the thing that executes the code. And the second thing is, ask the compiler for more info when you're doing source level coverage for level A. So how it works? How does project coverage work? We run the object code for the intended target. So you take your cross-development tool chain for your PowerPC or whatever processor, and you run it unmodified on an emulated target. And we use the Quick Emulator, which is an open source emulator, to run the software. For instance, just to give you an example of the power of QEMU, we can take VxWorks 6 or VxWorks 653 with an application on, and boom, run it under QEMU. So the emulator runs the target object code on the host, so you don't need the actual hardware to do that. And QEMU is instrumented to get the traces which are optimized for coverage. We don't need the full-blown traces. We need traces that gives us coverage information. These are saved on a file in the host, and the information is mapped offline back to the sources, either via debugging info, which you have in your binary. Dwarf today is pretty much a standard, thanks to info provided by the compiler. So this is the old way of doing things by instrumenting sources. Here's what we do, and I'll concentrate on this side. The approach is you take the sources, you compile them and link with your cross-compilation toolchain. You get an executable, which you can run on your hardware, or you can run it on QEMU, with an instrumented QEMU, which gives you binary coverage info, which you can complement with source info, either the debugging info or debugging info plus additional info for MCDC that the compiler generates, and you get coverage information.